Now we want to talk about actually computing the amounts of reactants and products at equilibrium.
So we've talked a lot about this idea of the value of the equilibrium constant and this sort of characterization of the equilibrium via equilibrium constant. That the value, that number, really is going to describe the amounts of reactants and products at equilibrium. And the thing about, we said the equilibrium constant is always positive, so the range is basically 0 to infinity. And we could take that whole range of possibilities and kind of divide it up into three kind of groupings in terms of describing what an equilibrium looks like. So first, we could have really small values of k, so less than 1,000, 0.001. And so these would be the kind of things where we would say that the reaction, the equilibrium is very towards the reactant or towards the left, because that's on the left side of the equation. So if we mix, say, this reaction where blue is our reactant and say it could become these red balls, because we have a very reactant favored equilibrium, if we mix all of our reactants together, we don't really make many products, right? The reaction does not really happen as we wrote it down. And so, you can write all the reactions you want, but they're not necessarily going to happen. So that'd be really small values. Again, it can't be negative values of k, but less than, say, 0.001 or smaller than that. And they can get very, very small. Then you get to these sort of intermediate values where, say, between 0.01 and about 1,000, where you have, say, your reactants, and they're going to products. And at equilibrium, you really do have both. You mix them together and there's a lot present. When we think about equilibrium, like this sort of mixture where reactants and products are both present in large quantities, this is really what we're talking about. Now, every single reaction does exist at an equilibrium, but when we talk about sort of the mixture of everything present, these are the reactions that we're talking about. And then finally, if you have really large values of k, so say something larger than 1,000, in that case, you put your reactants in your box, you let them react, and you get mostly product. Now, that being said, there will potentially be some reactant still present. The reaction does go towards products to the right. The reaction goes to completion. The reaction happens, right? And so when we've talked about reactions previously, using stoichiometry, using reaction coefficients, we've just assumed that this has always been the case, that you can write a chemical equation down and your reactants will become products, and you can just use the reaction coefficients to figure out how much product you're going to make. But that's not really always the case. For many reactions, that is the case, and it works great. And a lot of reactions that we've done, anything you've done in the lab has always kind of gone this way. A lot of industrial chemistry goes this way. But if you have these sorts of intermediate or small values of k, you're going to need to use an equilibrium description. You can't just use a stoichiometry calculation, a dimensional analysis calculation to figure it out. Either you have this full mix, or maybe you want to know how many of these red products you've made. There's not a lot of them, but there's some amount that have formed, and it's not what's going to be predicted, right? The stoichiometry was used for every one of these you started with. You got one of those. That's obviously not true. For every one of these, you didn't form one of those, right? So how much is actually present, you're going to need to use an equilibrium constant to figure out those relative amounts.
And so this equilibrium-based description is more accurate, but it's more complicated calculations, right? We'll get into that. We'll spend a decent amount of time, but we know that you start with, say, some amount of your reactants, and then you make at equilibrium some amount of product, but there is still some reactants present. And so this is a more complete description, that there are some reactants. You can figure out how much product you make, how many reactants are left, and it's a more accurate description, but it's more complicated. So an approximate stoichiometric description is you start with some amount of reactants, their concentrations go to 0, and all that's left is some product. So this will always be approximate. Using stoichiometry, figuring out how many moles of SO2 you have, using the coefficients, 2 moles of this gives you 2 moles of product, and converting that all the way through. So it is less complicated to use stoichiometry, but it is also approximate. So the question is, when is it okay? When is that approximation valid? When does it give you a reasonable result? So let's look at an example of, first off, when Kc is really large, because that tells us that the equilibrium mixture is mostly product. So for example, combustion of propane. Kc here is 10 to the 40th. Okay, so absolutely massive number. And so what that means is at equilibrium, there is approximately one C3H8 molecule for every 1 mole of CO2. So basically that's sort of, if you wanted to use an equilibrium description and figure it out, there would be 1 molecule left for every 1 mole of product. That means if you just use a stoichiometry analysis, your error is 1 molecule, right? Which isn't bad. That's extremely small, right? There's no way the sig figs of any of your numbers would at all represent that, right? You don't have 23 sig figs on your value, so 10 to the 23rd is going to overwhelm whatever 1 molecule error you have. That's why when a lot of times we write reactions, we just write them in single arrow. When you see a single arrow like that, you can assume that that means that that reaction goes to completion. We don't need to worry about an equilibrium description. Yeah, there is technically some reactant left, but it's so little that we just don't care about it, right? Who cares about 1 molecule of propane that's unreacted? We weren't measuring precisely enough for that to even know that that's there. If Kc is less extreme, for example, CO plus H2O becomes CO2 and H2, Kc is 10 to the 5th on this, so 100,000. It's not quite so dominant anymore. It's not so insane. So it is still product favored. You can see we still have the single direction arrow. Those reactants really do become those products. And so the error is about a 1 in 1,000. That for every 1,000 product molecule, CO2, there's about 1 reactant molecule that's left over. And so what that means is our stoichiometry answer has an error of about 0.1%. Not that bad. Again, not that big a deal. Generally, if you, say, put in 10 grams of CO and you want to figure out the mass of CO2 you get, you'll be fine using stoichiometry because it's going to be really close to the correct answer. One of the things we want to think about, though, is not necessarily just what is the error of our stoichiometry problems, but in real life collecting product. If your stoichiometry answer is off by 0.1%, that means your theoretical yield is off by that, right? What you theoretically could get, how much product you could theoretically get from all these reactants, because there is just unreacted reactant. This is equilibrium is one of the biggest reasons why you don't get a perfect percent yield, because there is some loss. Your stoichiometry assumed that equilibrium didn't happen, just it went fully to products, and that's not real. So if you want to make up for that 0.1% loss, you know, the fact that there is still some reactant that's present, you're going to need to use an equilibrium description to figure out how to control it, how much is left over, and how much can you get. There are also plenty of cases where Kc is very small, right? Kc is really small, 10 to the -6, 10 to the -15th, whatever like that. And so what that means is that the reaction, we would say, doesn't happen. And so you cannot use stoichiometry in any way, shape, or form when Kc is much, much smaller than 1, because you only form a small amount of product. It's mostly just reactant. The thing is, if, say, 1 in 100,000 molecules are reacting, that's not a lot. But if those molecules, say, are highly reactive or have high chemical reactivity or certain properties, they can really start to matter. For example, vinegar, CH3COH, you dissolve it in water and it reacts with water. And the equilibrium constant is pretty low, 10 to the -5th. This reaction doesn't really happen a whole lot. There's not a lot of product molecules that you make. It's mostly just reactants. So when you put a vinegar, this is acetic acid, when you put that CH3COOH in water, it mostly just is the reactant. It doesn't really change. And you don't get a ton of these products. You don't make a lot of H3O+, but you make some. And that is what gives vinegar a sour taste. That is what makes acidic things acidic. And so this H3O+, yeah, there's not a lot of it. There's a very, very low concentration of it. But importantly, there's some. And so because you get some of it, That means you are going to be driving the properties of the solution. You're going to be able to notice those when you're, say, observing it or, experiencing the properties. Vinegar tastes very different than water, and it's because of this H3O plus that is floating around in that solution. It's not a lot, but it's enough because that's some pretty potent stuff. Similarly, ionic dissolution, ammonium chloride, NH4Cl. This is something that we would have said is soluble because NH4 is in it, ammonium is soluble, and Kc is 30.9, which is greater than 1, which does mean this is a product favored equilibrium. And when you do it, you do get a 5.5 molar saturation limit. So yes, you can dissolve a ton of ammonium chloride. Lead 2 chloride would be an insoluble compound. We would say that this is not soluble. This reaction does not happen. It does not dissolve, but this is an equilibrium description. Kc is, again, small. It's 10 to the negative fifth. This is a low value, but there is still some product. If you put lead 2 chloride in water, some of it does dissolve, and that is a lead ion. And lead is really bad for people. And so you really want to be mindful of the fact that, yeah, a lot of it doesn't dissolve. The saturation limit is 0.016 molar. Very, very low amount of lead that's dissolved per water, but any bit of lead is too much. And so, that is a huge amount of lead. You do not want to be drinking that. And so the fact that there's any possible lead in that water is a bad sign, and that's something we really want to be mindful of. Let's look at an example of using our equilibrium constant, using this equation to determine amounts of reactants and products at equilibrium. So our reaction is 2NO2 becomes N2O4 at 298 Kelvin. Kc is equal to 170. Some NO2 is placed in a 2.0 liter container, and at equilibrium, 3.89 moles of N2O4 is present. How many moles of NO2 are in the container? What do we want? I want moles of NO2 at equilibrium. So if I want to get an amount at equilibrium, it's going to come from the equilibrium constant. And we know that the equilibrium constant equation is based on the reaction. My N2O4 is a product. It shows up from the top of the fraction. NO2 is a reactant. It's on the bottom of the fraction. And the coefficient 2 becomes an exponent. So then what I want is this amount of NO2. So Kc I have a value for, and I can compute my concentration of N2O4. We do want to note at equilibrium. So we can compute those, solve, get our information for the concentration of NO2.
All right, so we have this reaction. We're given some information on the equilibrium constant. Some NO2 is placed in a container, and at equilibrium, 3.89 moles of N2O4 is present. So how many moles of NO2? So this would be an example where we're actually starting to look at amounts of different substances that are present once this reaction reaches equilibrium. And so we put in some reactant, some of it becomes product, right? We're making some product here. And we just want to know how much is left over, how much NO2 is in the container in this mixture, because we know there's going to be some reactant and product present at equilibrium. So in order to do this, whenever we're trying to get amounts of things at equilibrium, it's always going to be based on our equilibrium constant expression, right? So that's why we're coming up with these equations. This is going to be the equation that we'll use to solve. It's going to be products. We have Kc. Do want to note, we're not, even though these are gases, if we were given Kp, we'd use that, but we're given Kc. NO2 squared. And so we want to think about which one of these do we want, right? Which variable do we want? We want this, right? We want moles of NO2, which comes from the concentration. And so the question is, do we have everything else? Well, Kc right there is 107. That's a number we would want to know. And N2O4, that's the concentration of N2O4. We're given moles. So we know molarity is going to be the 3.89 moles divided by 2.0 liters, right? So we do want to consider that that does need to be in molarity, and we get 1.95 molarity. So what that means is we can plug everything in. 170 is equal to 1.95. And then we have the concentration of NO2 squared. As much as it pains me to say this, it's generally going to be a good idea to not include units when you plug them in, just because, again, when we're working with equilibrium constants, the unit can be a little wishy-washy. We do have this labeled as concentration, so we'll know at the end our number is going to be in molarity. It's not just concentration, but molarity. Those square brackets always imply molarity. So we can rearrange our equation. This needs to get out of the denominator. That is 1.95 divided by 170. And so then that tells me that the concentration of NO2 is equal to the square root of 1.95 divided by 170, which is 0.107. And again, it's molarity. So that concentration, that answer that you get is the concentration. It's always going to be in molarity. So that is the concentration of NO2 that's left over in this container that you started with. We do actually want moles. So we want to take that and kind of go past it. So we know that we have 0.17 molarity. That means it is 0.107 moles per 1 liter, and we have a 2-liter container, giving us 0.214 moles of NO2. So we can figure out how much is present. You'll note Kc is, where is Kc? 170. So it is greater than 1. So we do expect more product, which is what we're seeing, 3.89 versus 0.2. But 0.2 isn't exactly a tiny amount relative to that, right? It's about a tenth, just less than a tenth of the product amount is that your reactants that are left over. NO2 is poison toxic, so it is mindful. We want to know that that is left over. It is a good idea. There is a real mixture of these things present at equilibrium. You don't just make N2O4 or just make NO2 to say NO2. There really are both of them there, and we want to be mindful of that, and we can compute those amounts. Kc is useful. If we have the value for Kc, we can describe any equilibrium for this reaction, and we can figure out how much stuff will be present. How many reactants, how many products. We can describe which chemicals we're going to have, and that's everything, right? That is how we do chemistry. We want to know what is present when we reach equilibrium. And when equilibrium is reached, Kc is going to describe it. But importantly, Kc, that value, does not determine how long the reaction will take to occur. So we know if Kc is greater than 1, it's a product-favored reaction. So all of these reactions I have listed up here all have Ks that are greater than 1. Some of them much greater than 1. But all of them are greater than 1, meaning products should form. If we look at this first reaction, it's propane and oxygen. When we mix propane and oxygen, that's putting propane into the air. They do not automatically react. You can mix propane and oxygen. You can, if you smell propane, right? If a propane tank releases, here's an example of, this huge propane leak. 30,000 gallons of propane is leaking, and you'll note it's not on fire. Right? It is, you're releasing this cloud and it doesn't catch on fire. It doesn't create water and carbon dioxide. You need to get this reaction started. The kinetics are really slow, right? The kinetics, you need a spark, you need a catalyst to get the reaction to start. Once you allow it, once you lower the activation barrier, you make a ton of products, right? It's very, very product favored. But just because they should form doesn't mean they will, and doesn't mean they will form quickly. Diamond, carbon in its diamond form, should become graphite. So carbon, that's diamond, carbon. That's both diamond and graphite are pure carbon, and so all diamonds should become graphite. Right? That is the more stable process. That is the preferred reaction that does occur. But the thing is, the kinetics are unbelievably slow. Under ambient conditions, graphite is the stable form. All diamonds are relatively unstable. They should become graphite, but it takes billions of years for that to occur. The rate constant is extraordinarily slow. The activation energy is incredibly high. And so it's just really, really, really functionally never, and kinetics just never happen. Solid, it's just a solid reacting based on, collision theory. We know that's really, really slow. Same thing, this bottom reaction with the Fe and the C, that's iron and carbon. That's steel. The initial formula is for steel. It should happen that if you have a piece of steel, it should just on its own become pure iron and carbon on their own. The equilibrium constant 10 to the 10th, very high. It really should occur. But again, it's just a piece of solid reacting that has a really, really slow kinetics. So this is not functionally that important for steel buildings. Steel is really strong. Pure iron is a lot weaker. You don't need to worry if you build a building out of, say, pure iron, that it's going to eventually become pure steel. You build it out of steel, it's not going to become iron and then fall apart. It's more likely just to rust in the air or degrade from salt, all sorts of other things. Other kinetics are much, much faster than this reaction. That steel should react and become iron and carbon, but it doesn't. It just takes way too long that it's functionally none of these reactions happen. Okay, participation 213, no questions in this video. Got a couple videos left, so looking for any more questions. See you in the next video.